as the humanoid botangelist under Going Ballistic 5. And if you go there, you will see this is pinned on my page. And it's a pretty good thread that explains a little bit about actuation strategies that we'd use in the hip. And you'll find out there's a collection of them out there. This is the long thread that kind of goes in, gives you some of the basics, understandings and nomenclature that we typically use, where I'm trying to clean up the nomenclature because sometimes in the robotics business, there's no agreement on what it is. So I'm borrowing heavily from biomechanics. And that way, if you come from a biomechanics background, you'll say, oh, I understand this. So there's others for not just the hip, but for the waist and the shoulder, looking at running gaits and everything else. So if you haven't seen some of those, they're pretty good. And the more or less like very simple primers to go through. It's not really super heavy, but it gives you the overview. Plus, there's a lot of videos that Marwa and I did along with them to kind of do deep breakdowns that run like an hour or 90 minutes, something like that. Okay, so some of you may be familiar to those videos and you may be familiar to my podcast location here in the background and everything. So today we are going to give a big overview over on actuators. And now I just need to make sure like my window just disappeared that I actually interact with. Like, give me a second here. All right, so we're on up here. So we can skip this one. And the first question is, what is an actuator? Anyone out there want to take that question?
Sure. In my opinion, it's just something that makes something move.
Yeah, basically. So it's you know, the definition there might be something like an actuator is something that actuates a joint. Okay, so kind of a strictly definition. My preference is just say it's a fancy name for a motor. Okay, and it basically can consider it like a sandwich, where the meat of the sandwich is your motor, and you have underneath it, you will have usually a reducer or transmission that takes the output of that motor and does something with it, usually slow it down. And then you also need to have some sort of controls in there, because a motor by themselves will just kind of spin and it's very hard to control. So if you want the position control, then you need to have something up there, which is going to be the electronics to control the positions of it. And like any sandwich, you know, if you have some really good deli, but your selection of bread and toppings is not very good, the sandwich will not turn out very well. So you need to make sure that you match all those things really well. Now, probably a better analogy is more like a bagel sandwich, okay? Because actuators tend to be round, and in some cases, they actually have a hole in the middle. So that's one way of sort of thinking actuator is just a fancy name for a motor. Okay, now, this is kind of what an actuator will look like when it's taken apart. So we can see in the middle is the meat. That's where the motor is. And there's many different ways of doing motors. You know, usually you have a stator section and you have a rotor section. And sometimes, usually the rotor is in the middle and the stator is on the outside. The permanent magnets are sometimes on the outside. In this case, you'll see they're, or the permanent magnets are usually on the inside, but in this case, they're on the outside. There's many different ways of doing it and still pull off the trick of being brushless. Now, over on the left side, and brushless basically means you're not trying to use little brushes which are rubbing up against the commutator. They're going to wear out over time and produce a lot of brush in order to get power from the outside to the inside. You try to do something so you can kind of avoid that. Now, usually on the top side is where you have your power electronics and encoders and everything else. And as you can see, the connectors is going to bring power and communication in. And then on the other side, the far side, there's going to be some sort of output shaft. And there's going to be some kind of reducer section in there that takes the spinning motion and reduces that down. And there's a lot of different ways of doing that. And so we're going to look into some of those as we go along. Okay, so here's kind of a close-up that we can get a better idea of what the power electronics kind of look like. Again, sort of an idea of what the motor sections are going to look like in there. And then over here, we also have the reducers. Anyone want to take a guess of what kind of reducers these are?
They look like Planetary.
Yeah, they are. And I believe they're multi-stage or two-stage, and we're going to talk about that, so don't worry about it. Okay, so I grabbed those things from Chen Yao, who is very active on X. If you don't follow him, I think you might, because every now and then he puts out a post that I find useful. and he works for My Actuator, which is one of those sources you can go online and like order one, and like probably within a couple of days you get the actuator you need for whatever project you're working on. There's one of many different companies over in China that are able to do that. Now, let's get into types of actuators. So, anyone have an idea of what types of actuators are out there? Want to take that question?
Planetary, cycloidal.
Those are reducers. So we want to actually just go right into the kind of actuators. So
Okay.
so we're going to get into that.
Linear, rotary.
Yeah.
Yep.
Rotary.
I think those are the
Mhm.
primary ones.
But yeah, those are the primary ones.
Prismatic.
Yeah, so prismatic could be considered linear. So it's like that's a fancy term for linear. And then you'll have revolute or rotary, which means it spins and rotates. And then a lot of times people may go ahead and bring in like hydraulic or pneumatic. And Randall, you're out there. You wanna mention something?
Yeah, no, that was exactly what I was going to say was the driving physics. Yeah, pneumatic, hydraulic, electromagnetic, all
Yep.
these different kinds of things.
Yes.
So it's like that
There-
that's definitely the broader category. And then
Yes.
from there it's like there's the geometries. Yeah.
Yep, exactly. So there's many different ways. We're just going to focus on electromagnetic. I mean, you don't have to be using magnets and electricity. You could be using anything else that is able to generate some sort of force or output. But we're not going to have water-powered robots or wind powered. I mean, someone probably will at some point, but we're not going to be thinking about that. So we're going to look at the two. And so basically, it is rotary or linear. That's basically the answer. And if you want to sound educated, you can say revolute or prismatic, and then everyone will think you attended MIT like Randall did. Okay, so here's an example of revolute and linear actuators that some of you may have seen before. This was about 3 years ago, I think, at the Tesla AI Day 2, where they showed the actual actuator classes that they've come up with and give you an idea of the classification of their size and the kind of output there is. Now, you notice that when you look at a linear actuator, usually we look in the output as a torque, right? And torque is Newton meters. And if it's a linear actuator, it's going to be force, and it's just going to be newtons. And for those of you who aren't familiar with newtons, we'll get to that pretty quick. Okay, so these are examples, and I believe we should be able to get this thing to spin. Oh, or maybe, yeah, there we go. So they actually had an animation on the AI Day 2, and you can find it if you just search YouTube. You'll find it. It's like a 3-hour video, and this is like somewhere in the first hour. And they give you an idea of the various components that are in there and how they actually work. So motors usually spin, and that means their output is usually going to be rotational as well. And there are some tricks you can do to take that rotational output and convert them into linear output. And then we're going to talk about how that's done. But in this case, Tesla is using planetary roller screws, and we're going to look at the difference between that and other ways of being able to convert it. And then they also have a transmission in here, which they call a strain wave. And if you're not familiar with that, that's also known as a harmonic drive. There might be like another term for it out there, but those, I think, the two most common terms that you'll hear. And then when you see how it works, you'll understand why it's called a strain wave. Harmonic sounds like very harmonious and like, everything is great and working really well. And the strain wave might be actually a bit closer. It seems like, it's really straining to do what it has to do. Okay, so again, these are the different kinds of configurations that we would see. And in here, if you don't want to look at the animation, I did a clip of a couple of the scenes in here, just so you can kind of see the breakdown of what's in there, what are the various components. And a lot of these components are going to be very important. So motors are going to need to have bearings because they're going to be receiving a lot of forces. And so sometimes the bearings aren't just to keep the axle kind of straight and make sure it spins really well, but you might have to have these cross roller bearings in there to be able to take loads that are coming from the radial direction as opposed to actually axial. So that has to be a consideration that we're going to talk about as we go forward here. And then, of course, you're going to need sensors and everything to kind of know where you are. That's the idea of an actuator. Is it's not just a motor that spins where we have no idea where it is. We actually want to be able to count revolutions and be able to precisely locate and position that shaft or the output shaft based on the information that we have. Okay, Types of reducers. So I think someone already was talking about what the different types of reducers are. We're going to quickly go through. Go ahead, Grant. Yeah, there's going as we go through the different families of actuators, it's very clear that why you might need one type over another. And so when you look at the different kinds of reducers, this is going to be very important on how you build your bot with the qualifications you want to have. So reducers, we've got several different types. So I think someone earlier mentioned Planetary, which we already saw. Another example out there is, of course, the Harmonics,
Harmonic.
Cycloidal, and then we're going to come to another one that some people may not have heard of. Yes. Okay, so before we actually get into that, we want to go through a couple of these terms, because it's very important to understand on their selection of the reducers how they affect these things. So backdrivable, backlash, QDD, torque transparency, and gear ratio. Who wants to take the first one? What do we mean by backdrivability? Yeah, it basically means if you take the output shaft and attempt to turn it, it will turn. So sometimes the gear ratios will be so high that it's virtually impossible to backdrive it, or you require so much torque. So it's kind of ironic that it's really easy in one direction to make things spin, but the opposite direction you can't. And so in many cases, you may or may not want them backdrivable, depending upon the application. The one thing that's nice about backdrivability is that if you run your motor backward, you might actually generate a little bit of electricity. So you could use that for energy capture in many cases. Backlash. Anyone want to talk about backlash?
Yeah, it's really a consequence of the way that the gear teeth mesh. Any kind of play between those is going to affect the.
Yep.
I'm not sure of the exact word, but the precision.
Yes, the position. So I'll let Jack take that one right here. If you haven't followed Jack X, you should, because almost every day he puts out a really good educational post about different things. So here's an example of something he just did the other day. So I said, oh, great. I don't have to go and search the internet for a good example where he explains exactly what backlash is. And it's just a natural consequence. When you build gears, they need a little bit of play in order for them to move. If you make them so that they don't have that play, they will just bind up and you won't be able to get them to move, or they just have so much friction. So backlash is part of what's in the system. Now, backlash in many cases is not a problem if your motors only move in one direction. You know, once the gears engage, and everything is kind of fine. But if you need to constantly reverse direction every now and then, you'll kind of lose your positioning accuracy momentarily until it picks up. And it's one of these things for very precise applications like CNC machining or something like that. You want to reduce the backlash as much as possible. And the amount of backlash you have will really depend upon the precision you have. Now, with humanoid bots, there seems to be this obsession about getting rid of backlash. And everyone's like questioning that right now and saying, wait a minute, we have all this sensory technology, and the humanoid is just kind of sloppy anyways. Why this obsession with the backlash? And maybe we don't have to be so obsessed. So this has a lot to do with the kind of reducers that you end up picking. Now, does anyone know what QDD stands for?
Quasi-direct drive?
Yes. So quasi-direct drive, basically you take the Q out of there and you mean direct drive. And what that means is that the motor spins directly the output shaft. So you've got a one-to-one kind of thing. You don't have any gearing or anything like that in there. And that may be okay for certain applications, especially if they're applications that you don't mind the fact that your output shaft is like running really, really fast. The quasi-direct drive is like you have a low enough gear ratio that it's almost like you are directly connected to the motor. And that kind of plays into the next. So does anyone know what we mean by torque transparency? Randall.
Yeah, like you said, yeah, that's really related to backdrivability and the gear ratio and the mechanical efficiency, because it's the goal is that by measuring the current or the torque that you're applying at the actuator point, you can understand what what the torque is, or at least closely what the torque is at the output.
Yep. Yeah. So you really know what's going on. And that way it's not kind of lost or filtered out. And the reason why I put gear ratio on the bottom is like basically all of those are determined pretty much by the gear ratio. So a small gear ratio means good torque transparency because you're basically a QDD at that point. However, the kind of gear ratio you have might affect your backlash, and will also affect the kind of back drivability you have. So like all things, it's optimization that's going on here, and you're going to have to compromise in one place or another. So if you lose torque transparency, it's not the end of the world. It just means you have to put another torque cell in there on the output to kind of measure what's going on and then see the differences between the two. So you can do it, but the preference right now is to get as close to QDD for control. Okay, now types of reducers. So we're back to the types. So this is the lead in. We understand a little bit what's going on. Now, when we look at them, we can start to understand the pros and cons of them. So the first one is the planetary gear. And does anyone know why that's the first one we're choosing? Go ahead, Jacob. Do you want to try? Well, partly it's the simplest, but the other thing is it's the oldest. I mean, it was around the time of Archimedes and maybe even before that. So we're talking thousands of years. Planetary gear systems have been known. And even the beginning of the Industrial Revolution, it was the go-to. And my mouse, there we go, get my finger off my mouse. And it wasn't until about the 20th century that we started to see other examples of changing outputs and coming up with different kinds of transmissions, partly because, automobiles coming in and also just needing to solve some of the problems. So it is definitely the simplest. It's very easy. We can produce these high volume. They have a little bit of backlash in there, but overall they have fairly good properties, but a lot of it will come down to volumetric density and how much room you have, because when we're building a humanoid, a lot of times we're concerned with like what's the overall size of our actuator, and sometimes the planetary gear might be too big. However, it's pretty popular, and as we'll see, everyone sort of shifted away from it, and now we're taking a second look at it. So even though it's the oldest and there are other replacements to it, everyone's coming back to it. So basically the way it works is you get a sun gear, which is the output shaft of your motor, which is spinning really, really fast, and you have these other gears, which are kind of the planets that go around, and you need to have a carrier to make sure they kind of stay in place and don't bump into each other. And then you have like the outer ring, and that ring gear is the one that is your output shaft, and it rotates very slowly compared to the sun gear that's going around. And if you can't quite get the gear reduction that you want in this, you can do what they call a multi-stage, that you basically plug the output of that into another planetary system, and then you're able to reduce it even further. Okay, now there's a version. I guess what I should do is go back here for a second and look at the teeth. So pretty much the size of your teeth are very important. If your teeth are too big, you might get too much backlash. So you might want to have your teeth a little bit smaller so they mesh a little bit better. But obviously, if your teeth get too small, they could easily break. And you don't want your teeth breaking, because once one tooth breaks, well, you've got to either replace that gear or throw the whole thing out. So you want to choose the size of your teeth just right. And of course, you've got to get your ratios and all that to make sure everything matches, because it's really the radii that sort of determines the gear ratio. Now imagine if I make the teeth smaller, or let's say if I increase the number of teeth that I want to have, what's going to happen to the size of the tooth? Formula is basically going to say the tooth gets smaller. Okay. Yes, it decreases. It gets smaller and smaller and smaller. So if I increase the number of teeth to infinity, what's the size of my tooth going to be? Basically zero. Okay. It's going to get so small. And then the question is, do I have an infinite number of teeth, or do I have zero? And that's where this next drive comes up that you may have heard of. It's Archimedes Drive from IMS in the Netherlands. And it's more of a friction kind of drive that also has zero backlash, because if you make the teeth smaller and smaller for a planetary gear, your backlash is going to reduce. It's going to get smaller and smaller. So you take it to the limit. And I'm going to look at this and say, man, that has zero teeth. And it's it kind of does, but at the same time, you could say it has an infinite number of teeth. One of the things that's nice about it is that even though it has zero backlash, there is a point where it slips, which is technically a lot of times what happens, that you don't want something like that, is that you get a torque that ends up breaking your system. So in this case, you really can't break anything. It will just slip. And there may be applications that when you get too much torque, you actually want the system to slip. for safety reasons and a variety of other reasons. You don't want it to bind up or anything like that. So this is an approach, very hardened steel. The precision requirements and everything kind of has to be packed in and under a lot of pressure to be able to get it to work right. So it's got application and it's worth looking at. There may be situations where it fits as something that you probably plug onto as an afterthought under your actuator. May not be a good idea, but if you actually design it into your actuator, you may be able to get the volumetric densities that you want to have and the same kind of outputs. So that's another drive that a lot of people have not known about. Yeah, go ahead, Randall.
Actually, I had a quick question. I remember seeing this drive in person and feeling the slip, and it was impressive. And it was, you know,
Yeah.
I can see how that would be a nice feature. And it's of course mechanical. You don't need a separate clutch. But
Yep,
one thing
yep.
I was wondering was why couldn't you just use a planetary gear and then have a current limit on the actuator side? Wouldn't that also limit the torque in the same kind of way?
Well, yeah, you can. So, but then that becomes more like a digital circuit breaker as opposed to like a mechanical or analog one, you know, and so we're going to have more and more safety systems that do that. Ideally, you would like to build everything that your system just is naturally safe, and you're not relying on the fact, is it powered up and is the software, the firmware running correctly? But there are a variety of ways of doing it. And I've also seen this in person, and anyone that's at the Humanoid Summit next week, you will have a chance to be able to see this as well and test it out. So that this is a variation of a planetary drive that you may have heard of before. And I did a video with Thibaut of Archimedes Drive back in June, and you'll be able to find it somewhere. It's on Marwa's channel. Okay, then there's the next, it's like harmonic and strain wave. And the harmonic drive is kind of interesting. If you look at it, you'll notice it's kind of elliptical. It's made up of three pieces. It's made up this interior part, which is sometimes called the wave generator. And it goes around and it's elliptical in shape. And between it and the output shaft is this thing they call a flexi spline. And it has like maybe like 2 teeth less than the number of teeth on the outside. And if you kind of look at how it's getting compressed in there, you can see there are places that there's no engagement with the teeth, and then the teeth slowly engage to the point that there's like full engagement. And the idea is there's like never any point in the system where the teeth are not like fully engaged in both directions. That means you can get rid of the backlash. You can reduce it. And there's like an animation that probably shows a little bit better of what's going on. So you can see why there's this thing called a flexi spline. And because you have a different number of teeth, you get this weird effect that actually is going to result on the blue part rotating. Now, they're not showing the blue part rotating out here, but it slowly moves with respect to the green one. And you can get very high gear ratios, 50 to 1, 100 to 1. And this is why everyone loves it, is because you can get very high gear ratios in a very compact area. But we do see there's this flexi spline, and it can be made of a variety of different materials that obviously have to be flexible. And now there's two things you can kind of see going on here. You'll notice that green thing that's going around is rubbing up against the red thing. Well, what do we call that? Anyone know what, when one thing rubs up against another thing? One surface rubbing up against another with relative motion? Yes, exactly. Thank you, Lee. We call that friction. And what's like some synonyms for friction? Well, one of them is inefficiency. Another is like heat. So just right there, that rubbing that's going on there, you know, wear and tear, abrasion. I mean, you can see a lot of, yes, exactly. So, you know, entropy, we can come up with a lot of words for that, but basically, yeah, noise, here we go. And then we've got the flexi spline, which is flexing, okay? And what's a property of flexing? And if you don't know, and if anyone has a metal coat hanger, take the coat hanger out and start flexing it right now and flex it for a while and tell me what happens. There's like two possible things that are going to happen. Don't overflex
like
it.
Plastic deformation.
Yeah. So one thing, when you do that, you take that coat hanger and go like this long enough, either that coat hanger is going to break. So you have to make sure you don't do it too much. But even if you don't do it too much, that it's going to break, right where you're bending it, it's going to get warm. So you've got friction, and then you also have flexion going on here at the same time. Now, there's different ways of making these things. unfortunately, the harmonic drives that I've actually seen them put into a lot of the humanoids, the flexi-spline is like more of a cup. And that's kind of weird. So, and that means that whole cup has to deform in a way. And so there's way more deformation going on that thing. And it's usually made out of metal. And then that outer part, that blue part, is usually made out of hardened steel. And it's very expensive to manufacture, and it takes a long time. So because you don't want to change the dimensions, you got to get the precision right. It's one of these things that you don't harden after processing. You harden the steel, and then you have to go and cut everything away. Because if you add too much heat in there, you're suddenly going to lose your dimensions. And that means it's a very difficult process to do. That can take a long time. So that's why strain waves and harmonic drives are very expensive, and there's very few companies that know how to do it and do it correctly. And when you want to ramp it up, it becomes a bit of a problem. One of the big problems that, you're talking about this is that this is producing heat. It's like another term for a harmonic drive. I would call it almost a space heater. It just produces heat. So the efficiency of these things, while you may see some things claim, they can be up to 80%, 85% efficient, depending upon the kind that you have and kind of industrial applications that typically go in, like, maybe CNC machines or something like that. But typically the actuators you're seeing out there, most of them are saying they might be up to 70%. And then you actually talk to people and say, well, maybe, but we're actually seeing more like 40 to 50%. And when you're saying 50% efficiency, you shouldn't be saying 50% efficiency. You should be saying 50% loss. Or if it's 70%, 30% loss. And that means the power that's going in, the watts that are going in, you're only getting 70% mechanical efficiency out. What happens to the other 30%? Anyone want to take that?
Heat.
Exactly. I mean, it's pure entropy. It's not being turned. If it's not being turned into mechanical output, it's not like it's being turned into electricity or something that's useful energy. No, it's that. And what's one of the biggest problems humanoids are having right now? Do you know? If you hear about how long the humanoids run and the reason why they suddenly collapse, yes, exactly. Thank you, Grant. Overheating problems. So right now, the biggest problem is figuring out how to get rid of the heat. And so there's all sorts of things in putting fans in and heat sinks and trying to draw it away. And the thing about that is that the best way to get rid of, you don't solve the heating problem by coming up with a better heat exchanger. You solve the heat problem by getting rid of the heat in the first place. All right? That's the approach I would take. Don't work on a better heat exchanger. Find out what's going on, and that's when you start looking at some others. So, for instance, a cycloidal, which is again like a very bizarre mechanism, is starting to be popular because it has like in the high 90%. And in theory, it looks like it might be pretty easy to make because the precision that you need for gears and stuff like that, you need grinding machines. That in theory, the tech should be a lot easier. But that yellow thing that you see in the middle there, it turns out you got to get the shape of that thing right and you got to manufacture right. So it turns out it's much harder to make these cycloidals. But if you can, they have zero backlash. They don't produce as much heat because they're very, very efficient. They have almost the same space efficiency. But the one thing about a cycloidal, and if you actually say, hey, Alexa, go buy me a cycloidal drive, it'll probably turn the text into a psycho dial, meaning like psycho, kind of crazy, because it is eccentric, as you can see here. So you have a shaft which is actually off center that results in, you see it cogging around there and these different pins and all that other stuff. But it's a really ingenious kind of design that has a lot of popularity. And the way to get, when you see eccentricity, when something is rotating off center, what does that usually do?
It's going to cause vibration.
Yes. Anyone that's had the overload on their spin cycle knows exactly what that is. And the way you solve it is you make two stages. You have one on the other side that's offset from it, and then they kind of cancel out, so you don't get the vibrations and everything else. So there are ways of being able to solve it, and usually cycloidal drives are like that. So it's starting to get a look from some companies, especially Foundation is very open that they're using it, and I think there's a couple of Chinese bot companies that are also doing the same thing. So it's something that's worth investigating and being aware of. Now, You can actually go and 3D print. So I think this is like an example from an open source. You can do it. And everyone that's 3D printed a cycloidal drive has found the thing breaks in no time. Right? Because the plastic cannot really handle some of the loads there. So if you're actually going to build one in reality, you have to use like, hardened steel and everything else. You can't use any soft materials in there because there's also a lot of rubbing that's going on. And again, that shape really has to be perfect. If the shape is not perfect, you're going to have issues. So there are pros and cons to that. Just, unfortunately, there's not a perfect reducer yet. Now, has anyone heard of this? The RV, also known as a rotary vector reducer. Okay, so Jacob, you have, which means you were one of the rarities, because I had never really heard of it until about maybe 2 months ago. And to my surprise, I was speaking with a well-known roboticist the other day, and he had never heard of it either. Okay.
So I have actually read about it because
Yes.
I'm working on a robotic arm myself.
Yep.
And I've read some scientific papers from Natesco, and they find them.
Yes. And if everyone's kind of wondering what it is, you can do a search on it and you'll come up and you get like, a recreational vehicle reducer, and it'll be like, not for what you think it is, or it'll be some sort of relief valve in plumbing, So I was like searching for it, and eventually get down there and you end up finding like a YouTube video like this that explains exactly what it is. It's basically a hybrid between a cycloidal and a planetary. That's the best way to look at it. So you'll see that in the front side of it, we've got what looks like a planetary gear. On the back side, we've got a cycloidal. And they've been around for a while, but they're only just kind of starting to be discovered in the field of robotics, which is surprising. So again, like I say, people who have been in the business for a while, they can tell you everything about harmonics and planetaries and stuff like that. It's like, what's this? And then when you tell them what it is, they realize, oh yeah, of course, that makes sense. All right, so again, we can kind of look how all these things get put together. In this particular case, what kind of reducer do you think that is?
Planetary.
Yes, it's a planetary, and it turns out it is a multi-stage. And the reason for the multi-stage is that they probably needed high torque, which means a higher gear ratio, and that means you're getting into, is it a QDD or not? Now, does anyone know is there a strict definition of what QDD is?
As in, it's usually it's like a 10 or 10 to 1.
Usually below 10. They will say gear ratio below 10. Others will say you can kind of get up to 20 and maybe get away with it. There's pretty much consensus that once you're above 50, it's not QDD. It just won't work out that way. But it's sort of like, we don't really know where that frontier is. The assumption is it's probably under 20. It might be a little bit higher, but most people prefer to not play above 10. If you can stay down there, you might be able to do it. That might change as we go along. So many cases, if you need the higher torque, you may have no choice but to do that. Yes, Randall.
Hi, I had two things. One was just a quick comment on the strain wave gears, that this is, I think, important for people to know, because I didn't know this until recently too, is that, on the one hand, they say that they have zero backlash, but the problem is the cup of that spline is really flexible, right? It has to be to do the bending. And because of that, it's not very torsionally stiff. And so even though there's quote unquote no backlash, the output is actually kind of it's somewhat weakly coupled to the input. So there is some flexibility there, even if it's not purely backlash.
Yes.
Yes. And then the other thing I had was just a question, which was why would anybody use the RV reducer? Like, I just don't know what the pros and cons of it are relative to the others.
I'm not quite sure. I guess it's like any kind of hybrid. It's either has the best of both worlds or the worst of both worlds. There seems to be, and maybe that's why there's a lot of people are not aware of it, because no one has found that it is useful. But I'm seeing it showing up in the supply chain. And it was one of those things I saw, like one of those JP Morgan reports that was talking about the humanoid supply chain, went down there, and then it was like listing it. It's like, and there's going to be like these RV reducers. I'm like, what? Wait, what? What is that? I better check that out. So it may be that there's some experimentation going on there, or there's some confusion because they're used in other fields of automation and not necessarily in the humanoids. So yeah, let's get on here. Now, this is an issue. This is why I like following Chet, is because every now and then there'll be a good question in there and he'll give a really good answer. So, okay, why go multi-stage planetary? That basically is how I know it was multi-stage planetary. All right, I was able to see the answer. Over harmonic seems like a perfect opportunity to cut one stage out. And harmonic for high precision application, planetary is more durable than harmonics and has better overload capacity. And again, the other thing that Randall says is, like, if your output shaft is kind of wobbling around a little bit or is a little bit weak, it doesn't matter that where the gears are meshing, that there's no backlash at the gears if you still have something on the output that is not going to be very good. So there is never the perfect one. You have to look at your applications, and from your application decide what's going to be best for your application. So that's pretty much what's available out there. Now, other kind of drives is that most of these things we're going to see for rotations. Yeah, and so overload capacity is that at some point you're going to apply too much torque, and you've got to decide what's going to happen. Is your system going to break? Is it going to be able to handle it because it's robust? And a harmonic drive can suddenly slip or ratchet, and which may or may not be bad. I mean, when something like that happens, it means, whoa, wait, suddenly I've lost the reference between my input and my output. So I might have to recalibrate that. Or when something like that happens, you might actually break a tooth. So there might be a mechanical failure, and the planetary might be able to handle that. The one things that planetaries, or I'll say harmonics, are kind of known to be not very good at shock and vibration. So if something hits it really hard, and that's going to happen, like your bot falls down, or your bot is running, bam, 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 bam. There's a lot of shock going on there. Or your bot is holding something that is just vibrating a lot. I saw this thing, this video of Optimus with a jackhammer, and I'm like, I wonder how long it's going to last with that, because that's a lot of vibration that's going right in there, and the question is whether your structure would be able to handle it. And so harmonic drives may not be good for that. And if you literally are thinking, I want to have a construction site bot, you may say, I got to go with cycloidal or something like that. Maybe that's going to handle it better, and then harmonics are not going to work. Okay, so linear drives. Basically, the idea of a linear drive is, how do we take rotary motion and turn it into something that's linear? And the classic way that that's been done for the longest time, and I think what I'll do is, I may or may not regret this. Let's go ahead and try this for a second here, is I'm just going to stop sharing, and then I think everyone can see me right now. I don't know, Mauro, if you can enlarge me, but basically, if you spin a nut on a thread, you see the nut translates. And I can either hold the nut fixed and spin the thread, and then I can get the thread to move, or I can get the nut to move, depending upon what my output is going to be. And so that works pretty well. But the problem, I think, is, as we all know, is if you take a nut that's on there, you'll notice it kind of moves around a little bit. So there's not a whole lot of stability. There's a little bit of slop. And the other thing is, there could be a certain amount of friction depending how tight it's in there. So you might need some sort of lubricant or something to make it better. Now, we all know ball bearings is a great solution for being able to reduce friction when you want to have two objects rotating around each other. And so this is sort of the idea of a ball screw bearing, is that the balls go in there and they recirculate around, and they basically are in the threads, and they produce a lot of stability, and they also get rid of the friction. So the nut is made out of something like that. They've been around for a while. They're really pretty good. Fairly easy to manufacture. Your threads are usually pretty big, but some people may complain, it doesn't quite have the precision that we need for the application that we want to have. So they may go, I got to go back to sharing here. Let me make sure everyone can see that screen again. Okay, so again, if we look at what's going on the ball screw now, we can see that there's ball bearings that are just circulating around. And again, so it basically, it's a moving ball bearing is the way to think of it. And get my screen around where you want to go. Now, the other way of doing this is something that we were able to see from Tesla, and that they showed this linear drive that they have, this planetary roller screw. And on the inside, the planetary rollers is basically the nut that's moving back and forth. And it's engaging against some sort of threads to be able to do that. And we'll take kind of a look at what's going on. So the classic way of a planetary roller screw is, you see, rather than having a ball screw, they have these very high precision threads with pretty complicated gears. And like, we could do almost an entire episode just on this. And as a matter of fact, we have, that allows you to get the precision that you need. Now, the cost of manufacturing one of these things is a lot more for whatever extra precision that you might be able to get out of it. In this case, this is the classic way of doing a planetary roller screw. But if you look at what's going on with Tesla, it's like, well, wait a minute, I don't remember seeing a thread like that. And it's like, you're right, because what they have is what's known as an inverted planetary roller screw, where the nut is on the inside of something. And that shaft where they have to create that thread on, that's even harder to produce than this one. So it's very easy. And, you know, anyone that's done any sort of machining, you know, you can take a shaft and easily thread it very easily. Like, you just run a cutter through that, and it's very easy, and you can make it very, very long. But when you go inside of something, it's a lot harder. And yes, there are taps that can do something like that, but they're limited to how far they go, and it's very difficult to get the precision. So that can be very, very costly when you want to come up with it. But they have very good precision, very low backlash, but their back drivability is not as good as a ball screw drive. So you have to look at that in cost. Now, what we come to, and I did a big long episode with Marwa on this, of what's known as the great rotary versus linear debate. So if you're building a humanoid bot, should you ever use a linear drive? And if you should, where should you use them? Or is rotary always the way to go? And that's a good question. And the answer is, it depends. So, again, if you go through the posts that I have out there with the pin, I think down in there, you'll end up finding in the thread a link to here where I talk about this particular debate that kind of came up because the belief was back in the spring that every single humanoid bot was going to need that planetary roller screw, which is very, very costly to produce, and you need lots of them just for one actuator. And that without it, it's like, you can forget it. It's like, well, not really. It depends upon whether your robot is using planetary roller screws or linear drives in the first place. So you have to answer that question. So there's already been an episode covering that. So let's get into actuator specs and have an idea of, like, when you're looking at an actuator, what's the most important property you should be looking for. So before I get into like an example of a spec sheet, so Randall and Bryce, you kind of thought about this when you're sizing up an actuator. What's like the thing? Okay, see, everyone's saying torque, power density. Yeah, probably like, as much as you are looking for like size and efficiency and maybe speed and stuff like that are all going to be important. The one thing that is going to drive it is your torque. All the others kind of come after the fact. So if you don't have the right size torque, I don't care if it's light, I don't care if it's fast, I don't care if it's efficient. If it's the wrong torque, it's not going to work. Okay, so
Well, the other big part is manufacturability.
yes. Man, I mean, but that's all kind of secondary. The first thing is that I've got to size the thing right. And of course, they're all intertwined. You might say, I need something that produces this torque, and you get something that produces that torque, and it's really heavy. And because it's so heavy, you go, oh, I don't have the right torque. I need to upsize the right torque now, or I can't afford it. But if you can afford an actuator and it's severely under torqued, then you're not doing yourself any favors either. So you've got to look at all those things, and they're of it. I mean, that is trying to come up with the perfect actuator. And I think Marwa said it best, you know, the name of her post on this, like, actuators suck. It's like, yeah, they do. It's like, we just the thing that can produce the torque at the speed that I want and the weight that I want and all this other stuff, but there are compromises I have to make. So here's an example. If you go to like a website in Zero Air, you'll go in there and you'll look at it, and more than likely you're going to see the main spec they talk about that they put up. There's always the torque. And you can look at the torque, and underneath it says, is that the weight that I need? Is that the kind of speed that I need? And everything else. And you can go along there and get an idea. Now, does anyone have an idea of exactly what torque is and a good example? Because if you see some things in here like 70 and 80 and 170, and I mean, that sounds like this awesome ratings for torque. So let's talk about that for a second and exactly what we mean by torque. And I guess, Marwa, if you can pop me back up big again for the group. Anyone have an idea what torque means? So if I say something is 50 Newton meters, what does that mean?
I think Jacob had a pretty good idea, but
Yeah, so you can apply 50 newtons of torque at a leverage of 1 meter.
Yes. So an example of something that's about a meter long is like my arm. Okay. If my arm is straight out and I want to lift something, and I'm applying 50 Newton meters back here in my shoulder, how much mass can I lift? Because newtons, most people are not familiar with newtons, right? So how do we what's the relationship between newtons and mass? Yeah, exactly. So the relationship between them is G, which we can approximate as 10 meters per second squared. So if you take 50, just divide it by 10, that means you've got 5 kilograms. So that means out at this distance, 50 Newton meters, I am able to hold what might be, in this case, this is, I think, 2 pounds. And so this is about 1 kilogram. So I would be able to hold 5 of these things. Or maybe, let me see, a jug of water. See, that's probably, that's in the order of about 2, something like that. So a couple of jugs of water, and that's about what you might be able to hold. So 5 kilograms, or for the Americans out there, about 11 pounds. So is that a true statement? If I have 50 Newton meters right here, I should be able to carry a payload of that much. Everyone agree with that?
sounds right.
Sounds right,
So-
really? Yes,
so-
Randy.
Depends on the angle. So if
So,
you,
Well, let's say it's straight out. Okay, so obviously if it's hanging down, then I don't have to worry about it. But straight out, so that means I'm perpendicular to the direction of gravity. 50 Newton meters back here. My payload could be 5 grams or 5 kilograms.
yeah, to be honest, I got this wrong in the first class, and it was a helpful correction. But of course, we forget about all the structure along
Yeah,
the way, the mass
structural.
of the structure and the mass of the other actuators that are down the link, down the
Yes.
chain.
Yes, exactly. So that's always a problem, is that when you build your bot, your actuators are having to carry the payload of all the other actuators to get out there. It's just like a rocket, it's that it has a lot of thrust, but the problem is that all that thrust is carrying the mass that it needs later on in the trip. And so you have this teeny pipe payload and all the structural and everything else. And this is the same problem. And this is why there's this obsession with trying to get the mass of your actuators as low as possible and to bring them as close to the center, or what they would say proximal. Bring them in. We don't want them distal. We don't want them way out there. So the closer they are, they're better. And then we try to reduce what they would call like the reflected inertia of what it's going to see. So my actuator that'll be way back here trying to hold it, it's struggling, and it probably would not be able to hold that amount of payload because it's got to hold the arm already. And if you don't believe me, all of you get up and hold your arms out and see how long you can hold your arms out without any payload. And you're going to realize, oh yeah, I'm getting, it gets pretty heavy pretty quickly. So you got to look at that and realize that when you're coming up with these torques, you've got to look at a variety of situations to decide what I'm going to need and what is going to be sufficient. And we will get into stall torque as well towards the end. That is something else, which is also an issue. Okay, so I need to get back to my share so everyone can sort of see what's going on there. Enough of the little show and tell there. All right, so here we are back. Okay, so you can go in here and decide, I want to choose one of these things because it looks like it has the right output speed and everything else. All right, okay, torque. I need torque, but I also need to have the right speed. Does 60 RPM sound good enough? I mean, I'm used to when I'm looking at motors and stuff like that, they're always like, 1,000 RPM or a couple thousand RPM. This seems pretty small. What is 60 RPM? Anyone have an idea?
60 rotations per minute.
Yeah, so 60 revolutions per minute. The other way you can think about it, it's like if you multiply it by 6, you get degrees per second. So that means that's 360. So basically 1 revolution per second is what you're able to get. About how fast do you think human joints move?
A bit slower than that.
Well, it depends. It depends. That's probably about average. There's some athletes who can go a lot faster than that, but for the most part, it's right around there. You know, if you're running, it might be a little bit faster. So that's about a degree. Yeah, so that's like 1 revolution in a second. That's pretty fast. Now, the other thing is like, should I be going for higher RPM for humanoid? I mean, really, really high.
I don't think
Well,
you need
let's say I
anything.
have an output shaft that's able to do 600.
That seems a little excessive.
Yeah. Okay. Now, what you need to think of is the speed should also be a function of the range of motion. How many joints in a humanoid, except for like the real weird ones that are putting out there, if you actually look at the joints relative to a human, are able to go much beyond 180 degrees? Full range of motion, plus or minus 90, something like that. There might be a few that do plus or minus 80, but for the most part, in the order of plus or minus 90, right? So if your range of motion is limited to such a small area, that means you have a very short stretch that you've got to get up to that max speed that supposedly your motor has. Which means the acceleration has to be very, very fast. Now, these motors are torque rated. They're not necessarily acceleration rated, but they're kind of related, of course. It's going to depend upon the mass that's there. So if you want to hit 60 RPM over a range of 180 degrees, your acceleration at a minimum has to be 120 RPM per minute. Basically a factor of 2. So if you do it in degrees, which is usually what I'm thinking of, if it's 360 degrees per second, your acceleration has to be 720 degrees per second squared. And that means right at 90 degrees, you will just hit your peak. At that point, you have to hit your brakes and you got to slow down. Because remember, there's the accel phase and there's the decel phase. So if you want to get to that cruise velocity, you need to usually have over like a range of 180 degrees, you need to have your acceleration usually 4 to 5 times what your actual velocity is. That's the rule of thumb that you use to get an idea. So faster doesn't necessarily mean better if you can't get up to that speed. Randall, I think you had a question.
Oh yeah, just a very quick one. I just remember in general, like especially when choosing other electric motors, on the one hand you have the spec for max speed, but of course that typically means 0 torque at that speed, no
Yep.
load, no load speed. So I guess in this case as well, right? You probably can't rely on actually the max speed that they're quoting, but some fraction of it, depending on
Yes.
what torque,
Yes.
what mass or torque you're
Yes.
applying at that
Exactly.
speed.
Exactly. And that's when you start to get into the spreadsheets here. So, I mean, the first thing you'll see is like, oh, that says strain wave. What does that mean? What kind of reducer? Just another word for harmonic. So if you see strain wave in there, you know that's what that means. You will see that they have different torque values. So sometimes the numbers they have there might be the maximum torque, or they might be the average torque or the rated torque. So you really want to think about what the rated torque is. The max torque, you don't want to design around that. You're just like, you know, what is it I really need for my application? And I know every now and then I'm going to need a little bit of excess torque, but basically it's maybe about half of what the peak torque is going to be. So you want to look at those numbers to make sure you have it. And again, exactly like Randall said, look at the speeds. Just because it talks about that speeds doesn't mean it can always do it. It's going to depend upon where it is in the cycle and exactly what the loads are at the same time. Just a review as well. Every now and then you will see these things have like an IP rating. I think somewhere in here they may talk about it. Another thing you look at is that you notice that the voltage supply is 48 volts. That's common on just about all these things. But don't be surprised if you start seeing them coming out at 72 volts. Anyone have any idea why they might want to be bumping them up to higher voltage? Yes.
To reduce current.
Less amps. Jacob, you're right. Less amps, smaller cables, but what does less amps also imply? Less heat. Yes, exactly. So if we can't solve the heat problem other ways, we will solve it by increasing the voltage. And a lot of people will be saying, yeah, but it won't be safe. And then it's like, okay, we know everyone's kind of cool with 48. They might be cool with 72. They probably won't be cool with 100. So, and I think there are actually a couple of robots out there, look, that I see are using like 62 volts already. So yeah, don't be surprised to see that changing. and that you might want to consider that as well if you're having heating problems. And again, the IP ratings, if you're not familiar with it, it basically means, and this is an intellectual property, it's ingress protection, that a lot of things that are going to be exposed to the elements one way or another have these different ways of being able to tell, like, for pinch points and stuff like that. A lot of times you want to make sure fingers don't get stuck in things, and maybe you don't want dirt and dust or grime or other things getting in there. And of course, you're always concerned about water and what kind of water exposure you're going to have everywhere to, like, it's not, if a couple of drops of water hit it, you don't have to panic, to whether you get hit with a water spray, right down to whether you can submerge it, and like whether you can submerge it for a long time. So the highest would be like a 68. So you start seeing motors of 68, that's great. Does not mean your bot has like an overall IP rating of 68. There may be other components in there that are getting exposed to water, or pinch points that are exposed, that fingers and stuff like that can go in there. But this is definitely a starting point. Okay, so here's like another example from my actuator where you can see the back end. You can see exactly what the connectors are going to look like in their series. And you also see the hollow shaft. Hollow shafts are very popular. Anyone know why?
You can route
Easy
wires
way.
through.
Yes, exactly. Cable routing. It's absolutely great. So it's one way of being able to get them in there and make sure but even though the cables are going through there, they may get a little bit twisted and they're going to be flexing if your actuators build up a joint. Okay. So again, examples of what they have, you go through, you can look at the voltage, you want to look at the rated speed and torques and the peak torque, and understand that when you're looking at the sheets. So familiarize yourself with these sheets and get an idea of what's important and not important. And of course, you're going to be looking at radius, overall volume, and weight, and how that's going to affect everything. So actuator selection, the first place to start with actuator selection, I'm quoting this oracle out here. This wise man who once said, proper joint selection is a pivotal part of any humanoid bot design. And that's your dad joke for the day. It's pivotal. All right. So if you're going to do that, the first thing you want to use is this principle I refer to as in-out. And that is, you want to kind of look at how important a particular joint is in your bot. And it goes anywhere from like being indispensable, it won't function without it, to needed, will kind of function, but severely limits its ability, to optional, that, it's not essential, but just makes things maybe a little bit easier. Useless, offers no practical benefit or purpose that anyone can figure out. And then there's toxic, it like actually degrades the performance with zero benefit. So a lot of times you want to go through and make the decision of whether things in there. So basically keep it in or toss it out, use the in-out principle. This is like a principle you can use on top of like the whole idea that the best part is no part. Well, how do you decide that? So you've got to use a principle like this. And this is an example that Marlo and I went through of like taking a pretend bot and going through and sort of deciding whether a particular joint had any value and how we would rate it. And the thing to remember, there's not like there's a right or wrong answer. They are kind of a opinion, and it's a good idea with the design team to go through and have everyone write theirs own down. And when you see something different, get into a discussion about that on why you either think it's a good idea or you think it's a bad idea. So like just starting from the head, we went down and looked at like the neck. You could have 3 degrees of freedom in the neck that are usually lateral flexion, extension, back and forth. And then what I like to say is like you have yes, which is the pitching this way, the no, which is the roll, and then like the side to side, which is like your maybe.
Są
And
to
deciding
dobre do wybrania?
how important
A
they
no
are.
to pójdę teraz.
Yeah,
A
yeah.
jeszcze muszę kupić może do spożywczego, bo oliwę.
Jacob, can you mute, please?
No
Okay.
teraz już nic więcej nie
Marwa,
zrobimy.
can you mute Jacob right now? Okay, thank you. All right, so again, do you need to have motion in your neck? It may depend on how your cameras are set up. It seems like everyone agrees right now that you probably need to have at least 2 degrees of freedom. But you always hear the arguments, well, wait a minute, can't we just put a bunch of cameras around there? Maybe you can. So that's what you have to figure out. Depends upon the design system you have. And you go in and you rate them. So you decide that. You do the same thing for the arm. You go through there. And the way to make the rating is for you to understand what every one of these things does. What's the purpose of every motion in your arm? Go through it and decide. Basically, your shoulder is all about pointing your arm in a particular direction, because what we want to do is you want to get your wrist to a place that you can actually manipulate or do something. And that means moving it somewhere in space. And your arm the shoulder basically points things to where they're going to be. The whole purpose of the elbow is to change the distance, the length from your shoulder out to where you need to be. So it's a way, if you think of this as a spherical coordinate system, it's your radius, gets you kind of out to where you want to be. And then, you know, out on your wrist is the stuff that gives you the orientation that your hand needs to be in. And you have to decide how important some of those orientations are to your hand for doing certain manipulations. And you'll see most arms have 7 degrees of freedom, which means there's a redundancy in there. So you could argue, oh, which ones do I really need, this joint or that joint? Could I get by without it? I've argued before, and as everyone notices, that your wrist joint doesn't move very far in the yaw. It has very little movement there. It's probably the least important of all the joints. So if you're going to throw a joint out, you might start there. And you say, yes, but how do I get my wrist to different joints locations? Well, that's because you get redundancy in your shoulder. And it turns out that extra axis in your shoulder is what will allow you to get it around. What the extra axis gives you is the ability to keep your wrist at a position, orientation, and space by getting your elbow in different positions. So that's why we sometimes call it the elbow redundancy. It allows us to rotate the elbow while keeping that hand in a fixed position, so I can get underneath somewhere to be able to do anything for accessibility. So the redundancy is not about reach, it's about accessibility. All right, so you go through again and again and make these decisions, which ones that you need to have. The ankle is a classic example of where you can find a toxic joint in there. And that is absolutely no one that I know of has the ankle rotate underneath the knee. It just doesn't seem to be needed. It's absolutely toxic. That rotation is actually done at your hip because it's like the hip redundancy that you have up there, which allows you to point your toes in a particular direction for you to be able to walk correctly. The reason why it's toxic is that if I need that rotation, that's another actuator, more cost, more mass. And it's the worst kind of mass. We're talking distal mass as opposed to proximal. So if I can get the rotation that I need of my foot pointing in the right direction up at my hip, that is definitely a winning strategy versus I'm going to put it underneath my knee. And that's going to be very, very costly. So you go through, you do that, and now you can start to decide your actuator placement and how you stack them together. And if you look at my hip post, I talk about the different orders of operation or ways of stacking your actuators together to get the rotation that you need at these different joints. You have a far hip, which we call flexion, abduction, rotation, or you can have an ARF hip like you see on the Tesla bot, which is abduction, rotation, and flexion. And there's arguments pro and con on why one architecture is better than the other, but everyone seems to be going with the FAR kind of approach. So once you've sort of figured it out, you've got to go through and then start adding up the masses of all these things and figuring out what the torque is. And that's going to be iterative because you're going to think I've got everything right. And then you're going to find out, oh, my arm is too much. So from Tesla, remember, they gave us these initial masses. I'm sure they have changed since then. And as a result, I just said, oh, this is a fun little exercise. I think here, this is like one of the last actuator they have for the hand. They didn't give a mass for that one. But you can go through and make a little spreadsheet where you can start adding up the number of actuators they have. And we could see from the bot, the placement of where those different actuators were, and just start adding it up and begin to get an idea of like, well, how heavy is the torso? How heavy is the arm? And all those. And from there, you can begin to estimate. I was like, well, if the arm weighs that much, how much torque would I need at the shoulder just to be able to do that? Assuming the mass of the arm was at the very end. Of course, it's not. It's distributed along the arm. So you have to really look at where's the center of gravity of that whole system to determine what that would be. But that's one way of going on to get an idea of what the overall mass of your arm, of your bot is. Now, I did this as an exercise to see whether Tesla was coming close to the fact that they wanted to have like 120 pounds for Optimus. And I had to make a bunch of guesses in there. And I think my guesses were a bit off because I think the first generation Optimus was probably around 70 kilograms or maybe a little bit more. So some things were easy to get, like the battery pack. You know the number of batteries, you can go out there and you can figure that out. And you know exactly how much maybe the actuators are. What you don't know is necessarily what the structure is. And probably I was like 5 kilograms for the like remaining structure. Was probably overly optimistic, which is why they probably end up coming around 7. And just about everyone's around 70 kilograms. It's been very hard to get under that, except for 1X, because they have a very different strategy. For an adult size, you can get one that's 35 kilograms if you're Hobbit size. But if you want to be full size, it's really hard to get below there. And again, it comes down to the mass of the actuators, because if you look at the overall mass of the actuators, you see they are a significant part, not only of the mass, of the cost. So,
What-
you know,
What different strategy are you referring to for 1X?
part of it is that they are using tendon drives, and with their tendon drives, they're able to move a lot of their actuators more towards the center. So they don't have as much distributed along the arm. So now that their arm doesn't weigh as much, their actuators don't have to weigh as much. That means their actuators can be smaller. Okay, so now they move it, they can make them smaller. And the fact that they are using capstan drives as opposed to gearbox, they also save mass there. So they don't have a harmonic drive or a planetary drive or anything like that. They're using a capstan. It's basically, you know, think of a pulley system where you have different size radii, different, but has the same thing. So you get gear reduction without the mass that's on there. So they've been able to get it down to like about 35 kilograms, which is amazing. But just because they took a very different approach. Yeah, Grant. Tendons are just finicky and difficult. I'm so glad someone's doing that, just like I'm glad to see Clone is using also a very different actuation strategy by using hydraulics. We don't know the answer. A lot of people who've tried it just gave up on tendons because they're just so finicky and hard to figure out how to control. And of course, a lot of that is people who were doing it 20 years ago when they didn't have the advantage of neural nets and some of the, you know, the new materials that we have. So, so Bernd is like, he is bound and determined. I mean, he's either persistent or stubborn. You know, the difference between that is someone who's persistent ends up being very successful. It's just because they didn't give up. Stubborn is someone that keeps on doing something even though everyone says it's not going to work. I don't know which one it is right now, but we'll find out. Right now, it's like maybe more towards persistent. Yes, Randall.
I wanted to be careful or to be anonymous, but I do know I have one friend who was apparently one of 3 people at 1X that designed the tendon drives and really understood them. One of the lead mechanical engineers, and even though he designed it, you know, and really did it, you know, really was proud of his work, he did feel like it was still overly complicated and too expensive and probably not the right way to go.
Yeah.
So it was interesting hearing his perspective, having been the one that designed it.
Yeah, it's a philosophical debate, and again, a lot of engineers are working on it probably see it as being very difficult, but then every now and then you get this visionary that just keeps on working the problem, and in the end we look back and just like, oh, give him accolades because he was able to solve what was the unsolvable. So it's good that there's always someone out there trying to take the contrarian approach. That's what I call not sailing with the fleet. Sometimes you go off in a different direction, and then maybe, I mean, at some point, I mean, remember Edison had, like everyone would say, like 1,000 failures before he figured out how the light bulb was going to work. So all that was good data points. And either 1X is going to tell us that tendons are folly, or they're going to tell us that, you know what, maybe this is the way of the future. It's just that you guys didn't try hard enough. But I would say right now, the easiest way to get results is probably the way everyone is doing it. It's definitely a lot more manageable. Aha, okay. And then Eduardo's got a third option, but he's not going to share. I'm sure. All right. So now actuators as joints. So the idea is like the easiest thing is that, remember, we've got to have things that joints that move, and we want to actuate it. And you don't necessarily have to actuate it at the joint. So the joint can be you know, something that's kind of passive and remotely activated, or you can go ahead and make the actuator the joint. Anyone think of what are the pros and cons of that? Yeah, 4-bar linkage is one way, but what would be one of the advantages of actually having your joint be the actuator? Mass. Okay, exactly. Mass is closer to the rotation, and you get a 2-for-1. You don't have to build it. It's just like less stuff. It's like, I got a thing that's rotating, and I also need a joint that rotates or a hinge. Why not use it there? So that's one huge advantage of it. Anyone think of what the disadvantage is? Yeah, basically all the stresses and strains that joint is experiencing is going like right through the actuator and right to the motor and everything else. So that means you have to fortify that whole thing. And that's why you have like cross roller bearings and all these other things, because, you know, even though if the output of your shaft is slow, the motor likes to spin fast. and you like to have a very small gap between the stator and the rotor. The smaller the gap, the more efficient it's going to be. But if your axle is experiencing a lot of heavy loads, there's always a possibility that it deflects, and then it's going to bump into it, and you don't want that. So you're going to do everything. So you got to make that thing a really mechanically stable platform, which can be difficult. Okay, so here's like one reason why using your actuators as joints could be very, very advantageous. And that is, this is something that Jim Fan talked about last January when talking about the Unitree bot. That was really the first display of RL walking and running. And he has this one quote that just stuck out to me. You know, simulation used to be an afterthought. Now it has to be part of the hardware design process. If your robot doesn't simulate well, you can kiss RL goodbye. Hardware simulation co-design is a very interesting emergent topic that only becomes meaningful with today's compute capability. Okay, that's very important. And Jim is in the enviable position that he can dictate to the hardware companies how they have to design their hardware to match simulation. 40 years ago, it was the other way around. I was like building simulations, and we were asking the hardware companies, like, gee, do you really have to build it this way to be easy? And they were like, buddy, get out of our way. We're building hardware here. You've got to, you know, if your simulator can't handle the way we design our mechanics, then the problem is with your simulator, not our mechanics. And so, you know, we had to up our game. And of course, part of the reason you want to simplify everything is it's not that you're not smart enough to figure out how to model it. It's like the computers are just too darn slow to be able to solve it if you go really deep into the weeds. So there's like this compromise. Now, RL, of course, is very, very important. And they're more or less saying the more you do it, and basically having it's much easier to model the entire system as if all your joints were the actuators. And remote actuation makes it harder. And especially if you have parallel remote actuation. Okay, so like here's an example of trying to build my bot out of actuators at the joints. And so on the left, we can kind of see figure, and basically every single degree of freedom in here is the actuator itself, right where it needs to be. Optimus has a lot of them there, but the F that you see right there, it's using a remote actuation strategy where it ends up using a linear actuator. So in many cases, you can do a mix and match, but the more that you actually build them in there, the happier it will be for being able to do RL. Now, here's an example, the counter example of what Apollo is doing from Apptronic. And now what I want you to see is that right where the red line and the green line match, that's your elbow joint. So right there is your joint. And the blue line is the actuator. So that's like the hypotenuse of your triangle here. And the length of that is changing. The other two are staying fixed. And we know with a triangle, if you change the length of one of the edges, the angles are going to change throughout the whole triangle, even without changing the lengths of any of the others. And you can calculate that using the law of cosines to figure out exactly what that is. And you'll see usually you have a long side and a short side on your bases down there. And the ratio of them can be very important. So the actuation is done with the blue axis, and it causes a rotation in the angle that's opposite the blue axis, or the blue edge that's there. Okay, now the result of that is you want to look at the actuator displacement. Now, so this is a percentage of the actuator movement. And that's like the amount of range the actuator can move to go from top dead center to bottom dead center. It doesn't mean from 0 to 100 in length, because at some point, the blue axis can't get too short. It can't be shorter than the green minus the red. Otherwise, the triangle falls apart. So the orange line that you see here is showing a linearization. So if your joint was actually a linear or a rotary actuator right there, then basically there's a one-to-one relationship between the rotation of that joint and the output that you see. These green lines that you're seeing here are showing the relationship between the output of the actuator and what's happening at your joint. And you'll see it's a nonlinear displacement. And the shape of that curve depends upon the ratio of, well, I say the B to A, which is like the red over the green. So at some point you can up the ratio, and you see there's not much difference between a ratio of 10 or a ratio of 5. So usually they're probably around 10. I mean, you can go 20 or 30, it's not going to give you anything, but then you start losing some mechanical advantage. The only reason to do it is it looks like you have a nice linear section in there. that's somewhere around 10 or 15% on one side or the other of what's going on, which may translate to somewhere around, I don't know, 20 degrees. So what ends up happening is you've got like the middle range of your motion, everything is good. So when I'm doing this with my arm or my elbow, when I'm in here, it's fine. But as you start to get out towards the very end, and everyone kind of knows this mechanically, when you get there, things start getting bad because the arm starts straightening out, the edges start straightening out, and you begin to lose your mechanical advantage. And what ends up happening is the closer and closer you get to that, you see that very sharp, high slope. The slope is almost vertical, and that's like an indication that, whoops, bad things are about to happen. So you don't want to be in that range because you start losing control. And what that means is that if you look at joint velocity as a versus the stroke, right in the middle of your stroke, it's nice and flat and everything looks good. But when you get to the extremes, top and bottom dead center of that thing, you begin to see the joint velocity kind of takes off really fastly. So if I'm trying to control my joint in the middle, I can do it very easy. It's like, basically the input that I'm giving is the output that I'm seeing. But when I get to the edge, just move the actuator a little bit, and some of the output moves a lot. And so it becomes very hard to control because it starts to go very fast all of a sudden. And you can look at the other way, is that you can say, okay, let's take a look at, now this blue line down the bottom is kind of like an ideal rotary actuator, right? Basically, it's linear all the way across. Joint degrees and velocity are the same. If my rotary actuator is going at 20 degrees, my output is going at 20 degrees divided by whatever the gear ratio is, 20 degrees per second or something like that. Doesn't matter where I am in my range of motion. So it's not affected by position. However, there's a big effect on the position of your elbow joint when you're beginning to look at it, and you get kind of these two different curves, which are pretty hard. One is like the actual torque. So what's funny is like the linear torque produces let's say the linear actuator produces a non-linear torque, and the rotary actuator produces a linear torque, which is kind of ironic. So your torque at the ends basically falls to zero. But ironically, the speed, I had to actually get rid of it up here in XL because it wanted to put it up at infinity. So I capped it at 20 degrees. Otherwise, the whole range of this graph goes off. So you see how that kind of falls apart. It's very hard to predict that. And this is kind of what Jim Fan is getting to. It's like, ooh, you get these nonlinearities that are very hard to put in your simulation, which is why RL might be a little bit hard to capture everything right. And then this is what gets even worse, is your precision falls apart. So you can have this linear actuator, which is extremely precise. But as you get to those ends, suddenly your precision falls apart. Versus a rotary actuator, where I go to great lengths to make it sure that its output is very precise, and its precision will be the same throughout the entire range of motion. I don't have to worry about it. And you'll see here, I only have a very small section right in the middle where I have the position. Now you can begin to see why Tesla had said, oh, we're not going to use those ball screw guys. We're going for these planetary roller screws, because we demand extreme precision to be able to get that output to be where we need it to be. So that's why you have to think about your actuation strategy and what's going to work better or not. Okay, now there is one thing you can do to help things out, and that if you look at the Tesla Optimus knee, its knee is a little bit different. It's using something called an inverted Herkins mechanism, which is a 4-bar linkage that has a really interesting property that there's a range of motion that's actually linear that comes out of it. And the result of that is that this is from a paper that when Dennis Hong was on the Thor project, and I think when he was at the West Virginia and not at UCLA, that you can use that and you can flatten the torque curve to make it more linear throughout the range of motion. So that means rather than having a 4-bar linkage like we were seeing in the Apollo elbow, if you go to this 4-bar Herkins design, then you can get a linear torque, and also like a slightly extended range of motion that works out a little bit better. And as a result, iron, you can see what looks kind of funny around its knee. You're seeing the inverted Herkins kind of poking up there. You can also see it in Tesla. And if you ever go for a walk at a construction site and you look at an excavator, you can see an inverted Herkins right there. Actually, it's a modified inverted Herkins, technically, is what it is. That's what that 4-bar linkage is, because what that means now is that scoop, the torque that's on there is consistent all the way through. So the operator doesn't have to deal with that fact. Plus, I think it gives slightly better range of motion. you begin seeing these things everywhere. You know, once you can't unsee it. That's what it's going to be for everyone. So I probably just ruined it for all of you. Okay, now let's get into some idle speculation where I literally got myself in a little bit of trouble. And Randall, you're going to have to help me out here because I think you helped get me in maybe out of trouble. But if anyone remembers the at the Tesla shareholder meeting, the Optimi were on stage, and you notice they were kind of swaying around. They were moving a little bit, and they had to stay there for a long time. Okay, not just a short period of time, but actually for a long period of time. And I was wondering a little bit about that, and everyone's thought, oh, that's like really cool looking, and it's like, well, there's probably a reason for it to do that, and that is stalling. You don't want the motors to stall, because if they stall, they're going to overheat. And so my speculation was that it was actually better to have them sway and move a little bit, and not actually have them fixed, because that would cause the problem. Okay, then it turned out I wasn't the only one who thought that, because in the comment section, a lot of people blasted me, said that's not the case, and then others that kind of said, yeah, it is. And so it went back and forth. And a lot of it is that if your motor is fixed for a long period of time, you can potentially overheat. And this is like one way to be able to get around that. And so basically I left it to Anand, because he was on the Tesla team. And he was like, well, it's an interesting take. And he's not quite sure that that necessarily would be a situation, at least not carrying the load. And pretty much the argument going on in there is that if you design your bot right, when you're standing up perfectly straight, in theory, you could have everything in balance, that you don't have anything under torque. That's the ideal world, because standing is not an inverted pendulum problem. It's not even a double inverted pendulum problem. It's like a triple inverted pendulum problem. So you can get yourself into like this metastable position where you can convince yourself that none of my joints are actually going to be experiencing any torque. They will be producing a little bit, and they may be swaying back and forth. In some cases, they may have to actually hold that. So if you design it right, maybe everything will be there. But clearly, when you have a load in front of you, if you're carrying something, you're suddenly your waist joint or your knees or something else are going to do that. And the other thing is, none of these bots are ever actually perfectly straight kneed. So it's like, yeah, if you're straight kneed, maybe that knee isn't experiencing torque, but I have a feeling it is. So it's very important to be able to get a little bit of that in there. Okay, so it's definitely, the idea is that when you're carrying stuff now you get the stalling, and you got to start thinking about, should we have brakes? And that may be a good idea. And some of the actuator designs out there do come with brakes optionally, and are looking at different ways to do it. Industrial robots do have brakes. You hear them, they go click when it starts, and then when they stop, they will do that. And so you can potentially have brakes, because that's going to be a source of not only just overheating, but just wasted heat or wasted power. It's like, I got to have this torque that's holding on whatever my payload is. Why can't I just lock it down mechanically in some way? So a brake is a way of being able to do it. That's something to kind of look into. And that's why you might see in some cases stall torque data. It's just like, okay, this is how much torque you can get in stall, and maybe how long you want to do it before you start overheating. So idling is something you want to kind of look at, and it's kind of very important. And you also want to go through these exercises of figuring out yourself. So if you're not familiar with the URDF format, you need to do that. These are basically, it's an XML sheet that allows you to bring in data that you can find like in a GitHub that's out there, to get an idea of what actually the masses and payloads are of various bots that are out there, to get the center of gravity to do the calculation. And what's neat is, like, in there, they actually show you the motor specs. Some of these things that are got highlighted here in yellow are showing at a hip exactly what the torque is that's going to be there. The other thing, one thing I don't like about UDRF is, for some reason, it's in radians, and it's just like, and then someone says like the limit is 3.14 radians. Like, do you mean 180 degrees, or do you mean 179.5? I don't know. So, all right. But with that, and the fact that they give you center of gravities or everything like that, you can come up with your own model very quickly. You don't need to actually use a simulator like IsaacSim or Mujoko. I've actually done that myself, where you can go through and get an idea that if you take like an arm or something like this from example here of the Unitary bot, you can calculate what the torques are when it's holding his hand up. So that's one exercise you definitely need to go through to sort of figure out not only what your torques are, but to find out what the situation is going to be, for your stall loads or something like that, how long you'd be able to do that when it's under gravity. So when you put that out there, as you can see, the center of gravity here moves. So you see that little ball, you can barely see it here. And you can see when the arm goes out, suddenly the center of gravity has shifted a little bit, and you can see the center of pressure down on the ground, which we want to keep between the heel and the toe. If it goes too far forward, we're going to lose balance and particularly fall over. So you can go through this exercise, and because it's an XML sheet, you can read it and almost figure it out yourself, as well as use a very simple XML reader in a Python script to be able to suck the data in if you want that. And anyway, so I pretty much want to end on this. And on this slide is, again, this idea that looking at different braking strategies and the fact that there may be other ways that are not necessarily mechanical or friction or clutch of some sort, because surprisingly, not everyone wants a brake, or the brake is too costly, or it causes too much mass penalty in this and that. But you need to consider that also in your design. And with that, I've actually made it through and did it in 90 minutes. Okay, so I will stop there. And at this point, one thing I want to do is wish everyone a happy Nicholas. And if you know it, today is the 6th of December. And so in Belgium, where Marlow is and around there, it's very common to celebrate the arrival of Santa Claus or Saint Nick, for those who didn't know it. And with that, I hope everyone enjoys the rest of the weekend, unless there's any closing thoughts or questions. Okay.
I just wanted to say thank you and good to see you again.
Yes. Thank you, Water. Thank you, Randall.
Thank you
Okay.
all.
Okay. Okay. You're welcome. Yeah. Bye now.